Hello, dear students. We start our lesson, ISTM 13, Basic Provisions of Metrology. 13.1, Definition and General Concepts. 13.2, Physical Quantities. 13.3, Classification and Main Characteristics of Measurements. 13.4, Classification of Measuring Instruments. 13.5, Choose of measuring instruments, and 13.6, Metrological indicators of measuring instruments. Write down to your notes the plan of our lecture, and we are start item 13.1, Definition and General Concepts. All branches of technology could not exist without the extensive system of measurements that determine both all technological processes, their control and management, and the properties and quality of products. The branch of science that studies measurements is metrology. Metrology is the science of measurements, methods, and means of ensuring their unity and ways to achieve the required accuracy. The unity of measurements is a state of measurements in which their results are expressed in legal units and measurement errors are known with a given probability. The unity of measurements is necessary in order to be able to compare the results of measurements performed in different places at different times using different methods and measuring instruments. Physical quantities, item 13.2, physical quantities. In metrology, for all objects of measurement, a single generalized concept is established, a physical quantity. A physical quantity is a property that is qualitatively common for many physical objects, but quantitatively individual for each object. A physical quantity, which by definition is assigned a numerical value equal to 1, is called a unit of physical quantity. The International System of Units, System C, SI, has 7 basic units: length in meters, mass in kilogram, time in second, electric current, amperes, thermodynamic temperature, Kelvin, luminous intensity, candela, amount of substance, mole. Write down to your notes 7 basic units of International System of Units. And we start item 13.3, classification and main characteristics of measurements. According to the nature of the dependence of the measured value on time, measurements are divided into static, during which the measured values remains constant, and dynamic, during which the measured values changes. In static, measured value remains constant. In dynamic, measured values changes. From the point of view of the general ways of obtaining results, measurements are divided into direct, indirect, cumulative, and compatible. Direct measurements are measurements in which the values of the size of a physical quantity are found directly from experimental data. Examples of direct measurements are the measurement of body length with calipers or micrometers, the measurement of temperature, pressure, etc. Indirect measurements. Measurements in which the required value is determined on the basis of a known relationship between this value and the quantity subject to direct measurements. Aggregate measurements. These are simultaneous measurements of many quantities of the same type in which the required value is determined by solving a system of equations obtained from direct measurements of various compounds of these quantities. Compatible measurements. These are simultaneous measurements of two or many quantities of the same type to find the relationship between them. And next item, 13.4, classification of measuring instruments. In accordance with the state measurement system, all measuring instruments are divided into three types: standards, exemplary measures and instruments, working measures and instruments. A standard is a measuring instrument designed to reproduce and store units of measurements with high accuracy in order to transfer its size to lower measuring instruments according to the verification scheme. Standards are divided into primary and secondary. The primary is the standard that ensures the reproduction of the unit with the highest accuracy in the state. The initial standard, approved by the state standard of Ukraine as the initial one for the country, is called the state standard. The standard copy is used instead of the state storage of unit and the transfer of its size to the working standards. The working standard is used to store the unit and transfer its size to exemplary measuring instruments of the highest category. Reference measuring instruments are measuring instruments or measuring transducers intended for verification of other measuring instruments and approved and as exemplary. Reference measuring instruments are stored and used by the bodies of the metrological service. They undergo metrological certification. They are present with certificates which indicate the metrological parameters and the category according to the state verification scheme. Reference measures and devices are intended for calibration and verification of laboratory and factory measures. Factory measures and instruments are used to test products. By design and nature of use, all measuring and control tools can be divided into three groups: measures, measuring instruments, measuring equipments, and measuring systems. Measure is a measuring instrument designed to reproduce a physical quantity of a given size. Finite measures of length, angular measures, etc. A set of measures is a specially selected set of measuring used in different combinations in order to reproduce a number of similar values of different sizes. Measuring instruments and tools are devices by which measured quantities are directly or indirectly compared with a unit of measure. According to the nature of the use of measuring instruments, are divided into universal and special viewposts. Universal measuring instruments are measuring devices equipped with scales and used to determine various values of the measured quantity. They are divided into the following groups: line instruments with vernier, caliper depth gauge, micrometric tools, micrometric insight gauge, micrometric depth gauge, micrometric thread gauge. Lever mechanical devices: clock type indicator, caliper indicator, level bracket, level micrometer. Optical mechanical devices: vertical and horizontal optimeter, projection devices, universal and instrumental microscope. Goniometers, gauges, templates, etc. Next type is special purpose measuring instruments. Special purpose measuring instruments are divided into the following groups: means of control of plane, straightness, horizontality, verification rulers, plates, levels. Means for measuring surface roughness: profilometers, profilograph. Means for measuring the elements of gear and worm wheels: gear gauges, crocometers, normal gauges, etc. Measuring plant is a set of functionally integrated measuring instruments and auxiliary devices placed in one place and designed to generate measured information, signals in from convenient for direct perception by an observer. The measuring system differs from the measuring plant in that it outputs signals of measured information in a form convenient for automatic processing. Next item of our lecture, 13.5, choice of measuring instruments. Means for measuring the linear dimensions of products are selected taking into account the following main factors: the production program, design features of the product and the accuracy of its manufacture, IT grade, the error of the selected measuring tool, and the cost of measurement. The IT grade determines the error of the allowable measurement. In the conditions of a single production, special control and measuring equipment is not used, and therefore the control of the dimensions of products is carried out mainly with the help of universal measuring tools and instruments, calipers, micrometers, indicator inside gauges, etc. In serial productions, the main means of dimensional control are limit gauges and templates, as well as semi-automatic measuring control devices. The measurement error should not exceed 20–30% of the tolerance value for the manufacturer of the product. Measuring instruments are characterized by a certain marginal error from several means of measuring the same marginal errors. One should choose such a device which is characterized by the highest performance, reliability, ease of maintenance, and the lowest cost. Metrological indicators of measuring instruments The main metrological indicators of measuring instruments are the scale division, is the interval between two adjacent marks on the scale. For most instruments, the division of the scale is constant. Such scales are called uniform. The scale division value is the difference in the values of the quantities corresponding to two adjusted scale marks. The range of indications is the range of values of the scale limited by its initial and final values. Measurement range, the range of values of the measured quantity for which the permissible errors of the measuring instruments are normalized. The measurement limit is the largest and smallest value of the measurement range. And you can see the questions for current control on the theme 13. Types and methods of measurements, types of measuring instruments, standards, exemplary measuring instruments, working means of measurements, measures, their purpose and types, features of application of measures, working means of measurements, tools, devices, converters, mechanical tools and devices, working means of measurements, optical measuring devices for linear size control, working means of measurements, and pneumatic and electrical devices for controlling linear dimensions. So be prepared to answer for these questions. Write down to your notes the conspect of our lecture. And now I want to show to you a video about physical quantities.
Quantities that can be measured are called physical quantities, like mass, length, time, and temperature. But what is a physical quantity? If a quantity possesses these two properties, then it is a physical quantity. Its numerical magnitude and the unit in which it is measured. If we say that the height of a student is 165 centimeters, then it is representing both the properties of a physical quantity, i.e. 165 is the numerical magnitude, while centimeters is the unit in which the height is measured. Remember, if we only state height as 165, then it is not a physical quantity, since it does not tell us about the unit in which it is measured. So it is a must for physical quantity to have both magnitude as well as unit. Physical quantities are divided into two categories: base quantities. Base quantities form the base or foundation of other physical quantities. In other words, the quantities are the basis with which derived quantities are expressed. These quantities are length, mass, time, temperature, intensity of light, electric current, and the amount of a substance. Derived quantities. Derived quantities, therefore, are those which are expressed in terms of base quantities. These quantities include area, volume, velocity, acceleration, force, pressure, momentum, electric charge, electric induction, etc. Before talking about the units which are associated with base and derived quantities, we need to know about the universally adopted system of units for physical quantities. This is to be noted that measuring does not always involve counting. Like if we need milk, we need to understand what quantity of milk is required. Similarly, to describe the physical quantities, a standard is required with which the quantities could be compared and expressed. This standard in physics is known as a unit. By that time, it was crucial so that the knowledge and findings with the advancement of fields could be shared universally by adopting some known standards. In this context, during the 11th General Conference on Weights and Measures held in Paris in 1960, a universal international system of units was accepted. This system is commonly referred to as SI, System International. Now, coming back to the base and derived quantities, we have understood about these quantities. Now, we will have a look at the units in which these are measured. Base units. The units used to measure base quantities are called base units. We now know that base quantities are 7 in number. But in what units these quantities are measured? Well, length quantity is measured in meter. Time is measured in second. Mass in kilogram. Electric current in ampere, temperature in Kelvin, amount of substance in mole, and intensity of light in candela. Derived units. The units used to measure derived quantities are called derived units. They are defined in terms of base units. We get them by multiplying or dividing one or more base units with each other. For example, the unit for area is square meter, and for volume is cubic meter, which are based in meter per second, acceleration measured in meter per second squared, force in meter kilogram per second squared, or termed as Newton, pressure in Pascal or kilogram per meter second squared, momentum in meter kilogram per second, charge in Coulomb or ampere second, and magnetic flux density in Tesla or kilogram per second squared ampere. Let's take a deeper look into these. How can we measure quantities, like lengths, with proper accuracy? There are several ways. Meter rule. It is used to measure the length or distance between any 2 points. As the name indicates, it is 1 meter in length, which, by convention, divided into 100 centimeters. Each centimeter consists of 10 small divisions, known as millimeter. Thus, the smallest reading that a meter rule can give is 1 millimeter, also known as its least count. To have accurate measurements using a meter rule, we must keep our eyes directly above the reading points. Measuring tape. It is used by carpenters and builders to measure a greater length, usually in meter, centimeter, and inches. This means 1 centimeter is the least count of measuring tape. The same as in meter rule. To measure accurately using a measuring tape, we must keep our eyes directly above the reading point. Vernier caliper. To obtain an accuracy of more than 1 millimeter in our measurements, we use a vernier caliper. It has a main scale and a vernier scale, parts of vernier caliper located on its jaw. A vernier scale has 10 divisions on it, and each division equals 0.9 millimeters. Thus, the difference of 1 main scale division and 1 vernier scale division equals 0.1 millimeter, and is taken as its least count. To gain accurate measurement, we need to find the zero error of the instrument, if present. This will help to achieve accurate reading by adding or subtracting the zero error value from the obtained readings. Screw gauge or micrometer screw. It is used to measure small lengths with greater accuracy than a vernier caliper. The least count of a screw gauge is 0.01 millimeters. It also requires us to find the zero error of the screw gauge to accurately measure the length. The zero error value will then be used to correct the obtained readings.
With what is meant by measurement? It is operation of determining the value of a quantity. What is meant by system? It is orderly combination or arrangement of components connected or interrelated to form a single unit for performing defined function. What is measurement system? Objective of measurement system is to give user a numerical value corresponding to variable being measured. It consists of sensing element, transducing unit, output conditioning stage. For example, temperature is physical quantity which is to be measured. Thermometer sense the temperature and shows numerical value on scale. Measurement systems not concentrate on what goes on inside. It concentrates only on output and input. Next part of this lecture is measurement characteristics. It shows the performance of instruments to be used. Measurement characteristics classify into 2 types. 1. Static characteristics. 2. Dynamic characteristics. Let us see what is static characteristics. The static characteristics of instruments are changes slowly with time or do not vary with time. Example of static characteristics are linearity, sensitivity, resolution, threshold, etc. 2. Dynamic characteristics means. This is referred to the comparison between instrument output and ideal output when the input changes with time. Example: speed of response, overshoot, fidelity. Let us see one by one static characteristics in details. 1. Accuracy. It is the closeness of the measurement to the true value. Accuracy is the ability of an instrument to show the exact reading. If measuring instrument having higher accuracy, have lower the error, normally shown in percentage of error, which of the full scale reading percentage. Error is equal to measured value minus true value. Accuracy depends on inherent limitations of instrument and shortcomings in measurement process. Accuracy is defined in terms of percentage of true value. For example, if pressure gauge of range 0 to 100 bar has an error of plus or minus 1% of true value, the pressure of 100 bar could be read from 99 to 101 bar. Also, accuracy is defined in terms of percentage of full-scale deflection. For example, if pressure gauge of range 0 to 100 bar has an error of plus or minus 1% of full-scale reading, The true value of a pressure of 100 bar could be read from 90 to 110 bar. Second characteristics is precision, defined as the capability of an instrument to show the same reading when used each time. An equipment which is precise is not necessarily accurate. In given diagram, first diagram shows low accuracy and low precision results. Second diagram shows low accuracy and high precision results. Third diagram shows high accuracy and low precision results. Fourth diagram shows high accuracy and high precision results. Third characteristics is range and span. Range is the region between the limits within which an instrument is designed to operate for measuring, indicating or recording a physical quantity, is called the range of the instrument. The range is expressed by stating the lower and upper values. For example, if temperature measuring instrument able to measure temperature from minus 100 degrees Celsius to plus 100 degrees Celsius, then range of that instrument is minus 100 degrees Celsius to plus 100 degrees Celsius. Now span means. Span represents the algebraic differences between the upper and lower range values of the instrument. For example, consider previous example if temperature measuring instrument able to measure temperature from minus 100 degrees Celsius to plus 100 degrees Celsius. Then span of that instrument span is 200 degrees Celsius. Fourth characteristics is linearity. When incremental changes in the input and output are constant over the specified range, most instruments are specified to function over a particular range, and the instruments can be said to be linear. By using this formula, find the percentage nonlinearity. Fifth characteristics is resolution or discrimination. Means the smallest change in input reading that can be traced accurately. Sixth characteristics is sensitivity. This is the relationship between a change in the output reading for a given change of the input. Sensitivity is often known as scale factor or instrument magnification, and an instrument with a large sensitivity will indicate a large movement of the indicator for a small input change. Seventh characteristics is dead zone, defined as the range of input reading when there is no change in output. Eighth characteristics is threshold. If the instrument input is very gradually increased, from 0 there will be a minimum value required to give a detectable output change. This minimum value defines the threshold value of the instrument. Ninth characteristics is hysteresis. Hysteresis exists not only in magnetic circuits, but in instruments also. Hysteresis is defined as the magnitude of error caused in the output for a given value of input, when this value is approached from opposite directions, that is, from ascending order and then descending order. For example, as shown in figure, the deflection of a diaphragm-type pressure gauge may be different for the same pressure, one curve for increasing and other for decreasing. The hysteresis is expressed as the maximum hysteresis as a full-scale reading. Causes of hysteresis are backlash, elastic deformations, magnetic characteristics, frictional effects. 10th characteristics is drift. Zero drift is variation in the output of an instrument, which is not caused by any change in the input. It is commonly caused by internal temperature changes and component instability. 11th characteristics is repeatability. It is the ability of the measuring instrument to give the same value every time the measurement of given quantity is repeated under the same conditions. Repeatability refers to a sensor's ability to give identical outputs for the same input. Precision errors cause a lack of repeatability. 12th characteristics is backlash. It is maximum distance or angle through which any part of a mechanical system may be moved in one direction without applying appreciable force or motion to the next part in mechanical sequence. Backlash can be minimized if components are made to very close tolerances. Next type of characteristics is dynamic characteristics. First dynamic characteristics is speed of response. It is defined as the rapidity with which an instrument responds to a change in the value of the quantity being measured. Second dynamic characteristics is fidelity. Fidelity of an instrumentation system is defined as the degree of closeness with which the system indicates or records the signal which is impressed upon it. It refers to the ability of the system to reproduce the output in the same form as the input. Poor fidelity indicates non-linearity of instrument. Third dynamic characteristics is overshoot because of mass and inertia of moving part. That is, the pointer of the instrument does not immediately come to rest in the final deflected position. The pointer goes beyond the steady state. That is, it overshoots. Thank you for listening carefully. To learn about sensors in details, watch my next video.
And now time of our lecture is finished, so I will see you on the next week. Goodbye, have a nice day.